Welcome to week 7 of our course. In this week we will focus on a new concept, that of compactness. To give some motivation for this idea, let's go back to the idea of connectedness. So the intuitive idea was to have something which is continuous, a continuous object which did not have gaps. So continuous objects without any gaps. So I'm just putting it in quotes because it's just an intuitive idea, and we made it mathematically precise using the idea of a separation. And we saw that with the property of connectedness, we had this very nice theorem, the so-called the intermediate value theorem, was an application of the connectedness property. And so for compactness, on the other hand, the idea of compactness has to do, so again the intuitive idea is to have something of finite size. So again I'm putting this in quotes because we will see that not all things of finite size will be compact. And the usefulness of compactness lies in the fact that these spaces are very well behaved under continuity, so of continuity of functions and convergence sequences. And by well behaved I mean they have they enjoy nice properties, for continuity and convergence. And as an application, we will see a familiar theorem from calculus, which is that of the extreme value theorem. And these two theorems, the intermediate value theorem and the extreme value theorem, are familiar theorems from calculus, and the first one is associated with connectedness, while the extreme value theorem is associated with compactness. So with that said, let us look at the definition of a compact space. So our first definition is that of an open cover. And so we start with a topological space X, and we say that a collection A of open sets U alpha is indexed by some set J. It is called an open cover or an open covering of X if X can be expressed as the union of all these sets U alpha in this collection A. And in this case we say that A covers X. And similarly, if we have a sub-collection B of this collection of open sets A, it is called a subcover if X can be covered by the sets which are only in B. So these sets U alpha are belong to this subcollection B in this case. So this is an open cover and a subcover. So for example, let us give a couple of examples. So if you take X equals R, then, and let us take A to be the collection of open sets A, B, where A and B belong to the rational numbers and A is strictly less than B. Then this is a collection of open sets, and we have seen that this is a subbasis. So in fact X is the union of all these sets A of these intervals A B from this collection A. So this is an open cover. It is an open cover, or A covers X. Similarly, you can have any topological space X with a subbasis that generates tau, subbasis S, then S covers X. This was the very definition of a subbasis. On the other hand, you can also have collections which have only finitely many open sets, and that too is okay. For example, if X is the set of natural numbers, and you can have A to be the union of, well, it is the collection of two sets O and E, where O is the set of odd natural numbers and E is the set of even natural numbers, and both these sets are open. These are open sets because the set of natural numbers is given the discrete topology. Okay, so this is with the discrete topology. So in general, any subset of a discrete topological space is open. So in this sense, the sets O and E are also open, and of course X is the union of O and E. So we see that we can have many different kinds of open covers, and the question is whether, given any open cover, we can extract a subcover which has only finitely many open sets, and this is the notion of compactness. So let us give the definition. Compactness. So topological space X, topological space X is called compact if every open cover A of X has a finite subcover B. So B is a subcollection of A, and B covers X, and B needs to have only finitely many sets from the collection A. So the set is called compact if every open cover A, this is the main catch here, that even if you consider any arbitrary open cover, then it must have a finite subcover. So a subcover of your given open cover which has only finitely many open sets. So this is the idea, the definition of compactness, and historically it took many years to come up with this the right definition of compactness, and as we shall see, compactness enjoys very nice properties in terms of continuity and convergence of sequences, as I mentioned before. Okay, so let us see some examples of compact sets, some easy examples. So in general, just as a remark, in general, deciding whether a space is compact or not is not an easy problem, but there are some easy cases that we can deal with using the definition directly. So the first example is that of a convergent sequence. So let X be a topological space, and xn n be a convergent sequence, say xn converges to some point x in x. So we can show that the set A, which is the collection of all these points xn, n belong to n, and the singleton set x is compact. So now to show this, we will need some characterization of compactness of subspaces, because we are considering A in the subspace topology. So let us see why A is compact. So let's see a proof. So suppose that A is an open cover of A, which means that A contains open sets in A contains open sets in A, so in the subspace topology of A. So for each open set U in A, there exists an open set V in the topology on X, such that U is V intersection A. So this was the definition of the subspace topology. So now the point X, if we consider this point X, which is the limit of this sequence Xn, then there exists an open set let's say U0 containing X, and so U0 is of the form V0 intersection A for some open set V0 in X. And by the definition of convergence of sequences, this neighborhood of X, which is V0, it will contain infinitely many points of the sequence Xn. So this implies that there exists a natural number capital N, such that Xn belongs to this open neighborhood V0 for all n greater than or equal to n, since Xn converges to X. And since Xn's are already in A, this means that Xn's belong to V0 intersection A, which is just U0 for all n greater than equal to n. So we have found an open set in the collection A, which contains all but the first n-1 points in the sequence. So now choose for each k in the set 1, 2 up to n-1 an open set uk in A, such that the point xk belongs to uk. And this is possible since the set A, the collection A, covers A. So now we have for the first n-1 points these sets uk, and for all the rest the set u0 does the job. So therefore the sub collection B, which is just u0, u1 up to un minus 1. This covers X because the first n minus 1 points belong to these sets and all the rest belongs to this set. So this covers X, and this implies that A is compact. Similarly, for our second example, if we take let X be a set and tau be a topology on X, which has only finitely many open sets, then X is compact, because any open cover of X will already have finitely many open sets. So because the available open sets, the number of available open sets is already finite, so it is obviously going to be a finite collection. So therefore, in particular, a topological space X with only finitely many points, is compact, because when you have finitely many points, the number of sets in the topology cannot be greater than the cardinality of the power set, which is finite. So this is our second example, and as I said before, having examples of compact sets is not so straightforward. And so before we go to more examples, let us see a couple of non-examples. So examples of sets which are not compact. So first one is that R with the standard topology is not compact. Standard topology is not compact. So why is that? So if you take the collection A, take the collection A of open sets of the form n plus 2, where n is an integer, and this collection of course covers X. A covers X because every real number lies between two integers of the form n and n plus 2. So A covers X, but no finite subcollection of A covers X. This is because if you assume to the contrary that there exists such a subcollection, so suppose B is a finite subcover, then B is of the form ni plus 2. So for finitely many i's, so I in say 1, 2 up to m, so you only have m sets of this form from the collection A, and if R is equal to the union of all these sets, I equal to 1 to m ni plus 2, you can take the maximum. This leads to a contradiction as there exists a real number R greater than the maximum of all these ni plus 2, where I is in this range 1, 2 up to m. So if you just take the maximum of all these ni's and take the outer range ni plus 2 and take any number bigger than that, You can also go the other way and take the lower bound and take a number smaller than that, and so you will find that R is not covered by this this subcollection B. So R is not compact in the standard topology. Similarly, the open interval 0, 1 with the subspace topology, again with the standard topology on R, subspace topology is not compact. So in this case you can take, so if you take A to be the collection 1 by n, the open interval 1 by n1, where n is a natural number, then one can easily check that A covers the open interval 0, 1, but there is no finite subcover of A. There is no finite subcover of 0, 1 in A. And I leave this as an exercise for you to show. It's not very difficult to show this, so I leave this as an exercise. Now further examples will require some theorems, and our first main example using one such theorem is that all closed intervals in R, again with the standard topology, these are compact, and this is known as the Heine-Borel theorem, which we will prove later. And a consequence of this and another theorem leads to the fact that all closed and bounded subsets of Rn are compact. And for this we will require the Tikhonov's theorem. So this is a consequence of Tikhonov's theorem. You can also prove this directly because this is just a finite Cartesian product, but Tikhonov's theorem says that the arbitrary Cartesian product of compact spaces with the product topology is compact. And we will also see a proof of Tikhonov's theorem. Here, what I mean by bounded, what do I mean by bounded? So a set is bounded, B in Rn is bounded if there exists a capital R such that B is a subset of the Euclidean ball with center 0 in Rn, the origin in Rn, and radius R. So again you are taking the Euclidean distance, and B is called bounded if it can be seen as a subset of such a Euclidean ball. So all closed and bounded subsets of Rn are compact. So with these two important theorems, we have many examples of compact sets, namely closed intervals in R and closed and bounded subsets of Rn. So before we go to these examples and these theorems, let us prove some useful properties of compact spaces.